class, good morning, everyone. In today's class, we'll just discuss about the importance of the basic equations of electricity and magnetism. In the last class, we discussed about the basic equations of electricity and magnetism. We have seen the basic Gauss law, that is a integration of closed surface E, that is equal to E into ds is equal to q by epsilon naught, and that is called Gauss law. And also we discussed about the second equation, this integration of V into ds is equal to 0, that is the Gauss law in magnetism. And also the Faraday's law of electromagnetic induction, which says that the electric field is produced by changing magnetic field, that is E into di is equal to minus dou phi by dou phi b by dt. And also we discuss about the Ampere's law, integration of V into di is equal to mu naught I, and this Ampere's law is actually valid for the steady current. And also we discuss about the modification of Ampere's law, which has been done by the Maxwell, right, which is done by Maxwell. So here we just again will have the importance. Okay, we just studied about these laws, right? What is the importance of these laws in our daily life, where actually we are using these electromagnetic waves? So for that, I will show you the video. You can just see the video. By that, you can understand what is the thing what you studied in the last class, where actually you are using in our daily life, right? So we just start. We'll start my today's class with the video, right?
Hello learners, this is CC Engineering. Today we're going to talk about another fun topic in physics. It is all about Maxwell's equations. The person behind the Maxwell's equation is James Clerk Maxwell. He's a Scottish scientist who was fond with geometry and mechanical models. He started with the ideas in the mathematics that other physicists had already established, but he put them together to create a new, complete understanding of electromagnetism. We mentioned the term electromagnetism, but what is electromagnetism? So, electromagnetism is the study of the electromagnetic force, one of the four fundamental forces of nature. It is the interaction between electric fields and magnetic fields. An electromagnetic field is a combination of two fields, an electric field and a magnetic field. Now, have you heard the three equations of Maxwell? Now let's talk about it one by one. Now, the Maxwell first equation is just a form of Gauss law. Maxwell's first equation states that the electric flux through a closed surface is proportional to the total charge enclosed by that surface. A closed surface, in this case, is just a surface of any shape that completely encloses a charge, like a sphere or any other three-dimensional shape. Mathematically, this equation says that electric flux is the integral of the electric field over the area of the surface, which is equal to the enclosed charge divided by the permittivity of free space. The permittivity of free space is a constant proportionality that we've used before that relates electric charge to the physical effect of electric fields. In simple terms, it is a physical constant which represents the capability of a vacuum to permit electric fields. If the electric field is constant over the surface, then the left side of the equation becomes E times A. Now let's proceed to the second equation. Maxwell's second equation is also a form of Gauss law, only with magnetic flux instead of electric flux. As we have discussed before, magnetic sources are always dipoles, which means it has a north and south pole, and the magnetic field lines leave from the north pole and return back to the south. When you're looking at how a magnetic field interacts with the surrounding surface, you see that the field lines that leave the surface out of the north pole must enter back through the surface to reach the south pole. This results in the overall magnetic flux being zero. Now let's move on to the third equation. Maxwell's third equation doesn't have anything to do with Gauss law. Instead, it's Faraday's law, but just slightly different. As you can recall, Faraday's law of induction says that a changing magnetic field will induce the electromotive force in a loop of wire. Maxwell's version is a more general, simplifying Faraday's law to show the value of that induced EMF. It says that EMF is equal to the line integral of the electric field over a closed loop. So with this equation, you can see the connection between a changing magnetic flux and an induced electric field. Maxwell's first and second equations were so similar, one for electric fields and one for magnetic fields, which he knew there must be an equation that complemented Faraday's law as well. If a changing magnetic flux produces an electric field, why is there not a complementary law saying the reverse? Why can a changing electric flux result in an induced magnetic field? Now, that will be answered in his fourth equation. Here, in Maxwell's fourth equation, he started with Ampere's law, which states that current through wire induces a magnetic field around a path surrounding the wire. Maxwell added what is known as the displacement current into Ampere's law to complete the equation. Mathematically, the displacement current is equal to the change in the capacitor's charge over time, and that is equal to the change in electric flux over time multiplied by the permittivity of free space constant. With the addition he made to Ampere's law, Maxwell's equations were complete, and using his laws today, we can see a pattern in the production of electric and magnetic fields. Did you know your washing machine is a product of electromagnetism? Yes, that is right. It uses electromagnetic induction that is included in electric motors used in a washing machine. Magnetic recording and data storage equipment such as tape recorders, VCRs, hard disks are product of electromagnetism. Aside from that, we also have motors and generators, electric bills and buzzers, loudspeakers, headphones, and many more. And you certainly
Now, I think that you got a better understanding of what we studied, the Maxwell's equation. Now, by keeping this fact into our mind, we just discuss in today's class the integration form, how we can derive this Maxwell's integration form, uh, and the resultant of this integration form can be the differential form. So here, so we are just deriving the Maxwell's differential equation. In the examination, he will ask you to derive the Maxwell's equations, right? So what we just start our today's topic with the deriving. So in the examination, he will ask you, the question will be like this: derive Maxwell's differential equations. Derive Maxwell, right? Differential equation, Maxwell differential equation, Maxwell differential equation by using integral form of the Maxwell, by using integral form, Maxwell integral form, right? So we'll just derive the integral from the integral. We'll just take the integral form of Maxwell equation, and from which we'll just derive the differential form, right? So first law is nothing but Gauss law. You already aware of this fact that the first equation is the Gauss law in electricity. So what is Gauss law? You already had the information, right? Integration of E into ds is equal to q by epsilon naught. This is the integral form, first Maxwell equation, or we just say that is Gauss law for electricity. Now this equation, let us keep this equation as equation number one. Now what we are doing is that from here we want to derive the Maxwell equation differential form, right? From the integration form of Maxwell equation, we are deriving the differential form, right? So how we need to derive? So let us consider if or let rho be the charge density, rho be the charge density. We are just taking the rho as the charge density, right everybody? Rho be the charge density, And what is this charge density? And let us consider dv, right? dv be the small volume, be the small volume, be the small volume. See, by seeing this equation 1, we need to derive this integration form into differential, right, form of Maxwell equation, first equation. So for that, we are considering let rho be the charge density and dv be the small volume. So what we are doing is that now you already aware that density is nothing but here mass by volume. Here, since we are talking about charge density, so the charge density, so this can be written as the rho is equal to charge density, rho is equal to charge by volume. Can I rewrite this as uh, charge by volume, right, everybody? Right. So this can be denoted as charge is denoted by Q, and volume, what we consider it as V. So what you can just say that implies rho is equal to Q by dV. Clear, everybody? Now, so Q will be equal to rho into dV. Can I write like this? Rho will be equal to Q is equal to rho into dV. Clear? Now, this is a small charge, right? We can consider this as Q is nothing but a small charge, rho into dV. dV is a small volume. Therefore, the here Q signifies a small charge. We want the total charge. So how I can get this total charge? In mathematics, when you talk about totality, so the total charge can be obtained by integrating this, right, over the volume, by integrating Q over the volume, right, V. So rho into dV. When we just integrate it, we'll get the total charge. So now instead of Q, what I can write? Integration, volume integration, rho into dV. This can be substituted in our equation 1. Now employs the value of Q, the value of Q, the value of Q can be substituted, can be substituted substituted in equation number 1. Clear, everybody? We are just substituting in the equation 1. So when you just substitute it in the equation 1, so what will get? What is equation 1? Integrations closed surface E into ds is equal to Q. So instead of Q, what you can write? Epsilon, take the epsilon naught. That is the permittivity, as you have seen, 1 by epsilon naught integration or volume integration rho into dV. Clear, everybody? Now, now you can just see this is actually surface integral. LHS is surface integration, and this is RHS is your volume integration. So what we are doing here is that uh, so I think that you just now you have written your M1 examination, wherein you studied about Stokes Gauss theorem, how to convert the surface integral into the volume integral. We just see to it, right? So here one thing that you need to remember here is that uh, this can also be written as this can also be written as integration of epsilon naught E into ds. Can I write it like this? Is equal to integration, volume integration, rho into dv, right? Clear, everybody? Now we are having the information, right? Capital D is nothing but displacement vector. So D is also rewritten as epsilon naught into E, right? Clear, everybody? Now epsilon naught into E. So here what we can write here is that this integration of by applying, see, integration of, now this epsilon naught E can also be written as D. So what I can write? Integration D into ds, which is equal to volume integration V into rho into dv. Clear, everybody? So now we need to convert this surface integral into the volume integral. So how we need to convert it? By applying. So what I'm doing here is that applying Gauss divergence theorem. Now what I'm doing here is that I am applying Gauss divergence theorem, right? So I think that you remember this, right? Gauss divergence theorem, which states that you can easily convert if this is the variables, right? Integration of a into ds, where a is the variable, which can be written as this can be rewritten as volume integration del, right? Del dot a into dv. This surface integration can be written as, right? This can be written as d del dot e. Del is the differential operator. So here, what you can write, hence what you can say. So here a here is nothing but we just resemble a with this d. So what you can write here, see, integration of uh, del dot a is what here, d. So del dot d, right, into what I can write here, dv, right? Clear everybody? This should be dv, right? dv, which is equal to integration, volume integration rho dot dv. So I think that now you got very clear idea. Now this is your okay. Now this can be, this is volume integral. This is also volume integral LHS, and your RHS is also volume integral. So dv get cancelled. So what it will be, del dot d is equal to, can I write like this, del dot d is equal to rho. Clear everybody? Now del dot d is equal, d you already had the information, right? Since d is nothing but d is epsilon naught e, right? Clear everybody? You can just see this, you can just see this, right? This is what actually we have done. So this can be rewritten as what I can write here, del dot, right? uh, Del dot e, can I write like del dot e is equal to rho by epsilon naught, right? Now this is the differential form which has been derived by using the Gauss law integration form. The integration form has been derived by the differential form. Clear everybody? So we have just taken the derivation of integration form and we just derived it to the differential form. So now again, see here, once again we just discuss about the Gauss law. We have just taken this, you can just see the, we have taken this Gauss law. The Gauss law first basic law is integrations closed surface area is equal to q by epsilon naught. This is equation number 1. So in order to derive this differential form, we need to consider some important parameters. So if rho be the charge density and dv is the small volume, then the charge density you are having, any density is given by mass by volume, right? Normally density is mass by volume. Once you talk about charge density, so rho is equal to, instead of that, what I can write, charge by volume. So charge can be represented with small q, and volume is what, small volume. We have considered it as dv. So q by dv, rho is equal to q by dv, implies q is equal to rho into dv. The total charge, see, we just talk about here small charge. So therefore the total charge can be calculated or evaluated by integrating. So q is equal to integration, volume integration rho into dv. So the value of q can be substituted in the equation number 1. So we obtain that surface integral e into ds is equal to 1 by epsilon naught volume integral rho into dv. And we got that d is nothing but here epsilon, this epsilon naught will go here. So epsilon naught e into ds is equal to volume integral rho into dv. The displacement, electrical displacement, is given by instead of writing epsilon naught e, you can just rewrite it as capital D. So this is written as integration of d into ds, volume integration rho into dv. Now applying the Gauss divergence theorem, any function which is a parameter variable is written as surface integral can be rewritten as del dot a into dv. So surface integration can be converted into the volume integration in this particular format. So this we got that the differential form of the Gauss law is del dot d is equal to rho, and d is equal to epsilon naught e. So del dot e is equal to rho by epsilon naught. So this is what actually we obtain. That is called first Gauss law. So now when we talk about the second one, see, I think you are having a, I think that you got a, you got some idea, right? Exact idea. So how we just started with the equation number 1, and how we are how we came to the integration form, how we have reduced to the differential form. Clear everyone? Now we just see this the next one, right? Clear? You can just Again, just read it. Second equation. The second equation is what is the second equation? You're already having aware of the second equation, right? Okay, right now the second equation we'll just see that magnetic in the magnetic field in the Gauss law in the magnetism can be written as B into ds is equal to 0, right? This is the second Maxwell equation. Now we just convert this is into surface integral into volume by transforming, right? Very easily. But now what we are doing, this is the integral form. We want to reduce this integral form into differential form. How we can reduce? By transforming. See, by transforming or changing, by transforming the surface integral, by transforming the surface integral, by transforming the surface integral into volume integral. So how we can just transform that? Just now we have uh, done that. So what is that? We have just used the Gauss divergence theorem. So volume integral. So the Gauss divergence theorem, you're already having a information, right? So anything that is in the form of like this, right? A into ds can be rewritten in the volume integral form, that is del dot A into dv, right? Clear everybody? So here A is nothing but here B, right? Here A is here resembles the value B. So now what I can write here is that employs the volume integration of this equation number one can be written as volume integral del dot B into, oh sorry, right, uh, here I will write, see, uh, del dot B, right? This is volume integral into dv is equal to 0. Clear everybody? So now as the value is arbitrary, right, you can just see the integral must be equal to 0. So this value is arbitrary constant, so we just write that since del dot B is equal to 0. Now this is a simple form of, see, we just started with this integration of B into ds is equal to 0. So by transforming the surface integral into volume integral, so this any variable which is in the form of A into ds, here B into ds is there. So we just resemble, we just compare this one, and we compared it, and we got that volume integral del dot B into dv is equal to 0. So this volume integral is arbitrary constant. So you can just write del dot B is equal to 0. Now this is the second equation, Maxwell equation. We have converted the Maxwell equation, which is in the integration form, to the differential form. The third Maxwell equation that we'll just see here is your Faraday's law of electromagnetic induction. So what is that equation? C. Your third equation, E. This is your third equation, right? That is Faraday's law of electromagnetic induction. So which says that the electric field is actually produced by the change in the magnetic field minus dou phi B by, see, B by dou T. Now you are having the concept that you are aware of the concept, the magnetic flux density, the magnetic flux density, magnetic flux density is given by B is equal to, there's a formula of magnetic flux density that is given by flux by area, and this area is nothing but in the terms of uh, representative what you can say denotion, that is ds. So here implies what you can say, the flux is nothing but, just now we have seen about the flux, right? Flux is nothing but B into area by cross multiplication. This area is nothing but, we are talking about, if you talk about surface area, that is given by ds. So the total flux, the total flux, so the total flux, again this is informative parameters which is there in your intermediate. So phi b is equal to integration of, this is actually phi b, the total flux. When I talk about totality, we just integrate, we just use the integration form. So this is given by b into ds. Here phi b is a small is the flux, right? The total flux is given by integration, surface integration b into ds. The total flux is given by, so we just started our basic derivation with the Faraday's law of magnetic induction. And what we have done is that we just substitute our value of this phi b, right? This is this phi b value we are substituting in this equation number 1, right? This is our equation number 1. Now again we'll just rewrite that, right? Substituting substituting the value phi b in equation number 1. So we just substitute that thing in the equation number 1. So here you need to apply here what we are doing. You just see now integration of well, you see, first of all, integration of, all right, we'll write here integration of E into di is equal to minus, right? So what I can write here, integration of 5. So this can be written as right, dou b by dou t into, so this is in the numerators into ds. So this is what we are having. So this is actually line integral, and LHS, you can just see this LHS is a line integral form, and this is your RHS in the surface integration. So LHS is in the line integration and RHS in the surface integration. So we need to convert either LHS or RHS into same integration. So what do you have to do? We need to apply the Stokes theorem. Here what I'm doing here is that applying, see, applying Stokes theorem. So when you apply this Stokes theorem, so what will happen, right? So we can convert it to one of the LHS or the RHS into a similar form, right? So what that Stokes theorems, as you apply the Stokes theorem, so what will happen is that your E into integration of E into di, the line integration. Here the line integration, it can also be written as surface integration of del cross E. You already read dou phi by dou t can also be written as E. So what you can say, that is in the surface integration into ds. You can just see this minus dou phi by dou t can be written as here E. So what I can write here, so for del cross E here, this can be converted. So del cross E is equal to minus dou b by dou t, right? So here we say that this can also be written as curl E. This is a differential form. Curl E is equal to minus dou b by dou t. Now this is equation of the Faraday's law of electromagnetic equation in the differential form. Curl E is equal to minus dou b by dou t. By here we have used the Stokes theorem, right? So with this, I'll just take a leave for today's class. So again, we'll meet on the next class. We'll just discuss the last one, that is the Ampere's law, how we can convert the integration form of the Ampere's law to the differential form. Thank you, everyone. Thank you for your patience.